So this is the unit number 2 we are discussing about. Unit number 2, lecture number 6. So we are going to discuss about the structural modeling. Structural modeling. So this is the very essential modeling style we have to learn, because in the previously we have thought that only 3 modeling styles that we have seen. One is basic class, or in orientation class we have seen that the gate level modeling, data flow modeling, and behavioral modeling. So only these 3 modeling styles that we have seen. But there is another thing is called structural modeling. It is similar to that of the gate level modeling only. Okay, what the gate level modeling will do, it will take the gate primitives. Okay, it takes the gate primitives or built-in primitives. So with the help of built-in primitives or generally a primitive, we are going to connect these primitives in order to form a certain kind of circuitry. Okay. But instead of the building blocks, basic building blocks like primitives or built-in primitives, we have to define the component and make use of that one. Okay. So what do you mean by this one? I'll tell you. I'm writing here. In gate level modeling, we use built-in primitives. This is a statement we can call it as built-in. Okay, so therefore by using this, by making the interconnection of these built-in primitives, we construct some kind of digital circuit, and we are going to describe that digital circuit. That's what we do. Okay, why it is called a built-in primitive? Its definition is already available, right? Whereas in the structural modeling, it is similar to that of gate level modeling. Okay. Gate level modeling. Okay. So, but what we do in this, what difference when compared to the gate level modeling? That's what we need to know. So instead of the gate primitives, oh sorry, I think it has gone somewhere. Just wait. I think something has happened. Yeah. But here we use components. Okay, it's not a primitive, it's a component. Component means we have to define its definition. We have to define its behavior. Okay, so then only we have to write the structural modeling. So it is interconnection of the components. So here we use components. Okay, so the component means its definition we have to define clearly, and the interconnection of these components are nothing but structural modeling. So whenever we are using the components to make a digital circuit, the interconnection of the components, if you want to describe, we have to use structural modeling. Is it clear? So therefore the components are required to construct the digital system. The system consisting of the component, if you want to describe it, then we have to use structural modeling. Okay, fine. Now let us consider what do you mean by this one exactly. So with the help of example that we can understand. Okay, so take an example. You consider, for example, 1-bit full adder. 1-bit full adder. As we all of you know that what is the 1-bit full adder? Actually, it takes the 3 input signals and it will add all these 3 input signals. It will produce sum and carry signal. What is the gate level circuit? As all of you know that 2 exclusive OR gates are required, 2 AND gates and 1 OR gate is required. As all of you know that that is purely gate level modeling. Okay, that means the built-in gates are available in that one. I hope that you can understand. In the previous class, we told that, yeah, better I will write this one also. For example, you consider this is a 3-input exclusive OR gate. For example, 3 input I'm considering. So A and B, A, B, C.
मुझे क्या पता जो याद नहीं आलू है इतना पता है तो आलू टमाटर
Okay.
क्या होगा वर्कर्स के लिए ही ना बनाना है आलू टमाटर होगा अभी 1 घंटे नहीं जाएगी ना बिजली कम से कम अभी चली जाएगी नहीं जाएगी भैया शान ना हो रहे भैया
Yes, I removed that person. Okay, fine. So this is the circuit actually. Okay, it consisting of A, B, C, something like this, and everything we can write it there. Okay, so whatever the gates that we are considering here, these are called built-in, built-in gates or built-in primitives. We can call it as a built-in gates. Better we need to call it as primitive. Okay, so therefore it is a construction of the gate primitives or built-in primitives. But my requirement is that I don't want to use the gate primitives directly, something like this, but I want to construct the full adder using half adders. Right. So therefore 1-bit full adder using half adders. Right. So in that sense, what we are doing is that, okay, we take 1-bit full adder is something like this, having 2 input signals, sorry, 3 input signals, A, B, C, and some signal, SUM sum I'm using. This is called C out I'm using, right? This is the full adder, FA. My requirement is that I want to construct with this full adder using the half adders, right? So therefore, what I'm going to use that, everybody knows that in the digital electronics. Okay, I have a half adder here. Okay, I need to consider the input is called, inputs are A, another input is B. From this one, I'm going to develop sum 1, for example, sum 1, and it produces C out 1, it is producing. Okay, so I'm going to consider another half adder. Okay, so just connect this some signal as input.
Find the roots of the equation using bracketing method.
On the rule number 7. Okay. So I'm going to roll number 7, Sandeep. Somewhat somebody is okay. Next, this is called sum signal. Okay, we are taking the carry signal. Carry cannot come directly. This is called CO2, for example. Okay, I'm going to use one OR gate here. I'm going to OR gate here, connect from carry of this one, and take the carry. Sorry, I'm extremely sorry. This is not connected here. So the CIN is coming outside. Okay, CIN is coming outside. C. Okay, but now CO2 is coming from here to here. Okay, this is what I can say that C out to C out. So this is actually This is called C out. So this is called CM. Roll number 7, and then what is its roll number? Roll number 25. Removed. 725. Okay. Fine. Okay, so now this is what the inside of your half adder, sorry, full adder. Is it clear? So what is the full adder consisting of? So not only this direct to the gates that are available, it is also possibilities there. This is the half adder HA. This is half adder HA. I'm using the half adders to construct this one. Okay. Now the question is that, as all of you know that this is a built-in primitive. Okay. So the OR gate, built-in primitive, OR gate is actually built-in. So that means its operation for the an OR gate operation is already known to the compiler or a simulator. Synthesizer and simulator knows that very well about the OR gate because it's a primitive, gate primitive, or it's a built-in primitive. But half adder cannot, it cannot be identified. So therefore, what we have to do, so this half adder we are treating as a component. So we are treating this as a component. Therefore, we have to we have to define what do we mean by a half adder is. That's what the first thing that we have to do. Is it clear? So therefore, it is the interconnection of the components. Whenever we are using the interconnection of the component, then it is advisable to write a Verilog program based on structural modeling. Clear? So with the help of this one only, it is possible to do this one. Okay. So for that one, first what we have to do, first we have to define what do you mean by half adder is. Okay, clear? Shall we write? Okay. So shall we write now first half adder? So the half adder we need to write first. Half adder. So what is the half adder here is that we have two signals, for example, X and Nano, Y. For example, this is the sum signal, and this is called carry signal. For example, this is a half adder. Okay, so how a half adder can be defined by using the, so far we know that gate level modeling only. That's the reason why I'm writing the gate level modeling of the half adder. If you know the data flow modeling, if you know the behavioral modeling, it's fine. But so far we have discussed only the gate level modeling. Therefore, I'm interested to write in gate level modeling for the half adder. So therefore, we'll write module half adder HA. HA, I'm writing the name. Underscore gate level modeling is GM. Gate level modeling I'm writing. That's the reason why GM I put. So there is no space between this one. So instead of space, I'm using the underscore. So X, Y, sum, carry. So out of all these things, inputs are X comma Y. Outputs are S comma C. Okay. So what is the gate level modeling? So what is the gate level? Everybody knows that gate level modeling for this one is it requires one exclusive OR gate. Okay. So that is called as it requires one AND gate. So this is A, this is B, this is called C. So by writing this is X and this is Y. Okay. So this is what the inside of your half adder module is. Okay. Therefore, I will write an XOR gate. This is called G1, for example. This is called G1. Output is S. Input is X comma Y. I'm going to consider an AND gate. G2. C out C comma X comma Y. Okay. Finally, we need to write AND module. Okay, so this is how I have defined the half adder, something like this. I hope you can understand this one. Half adder, I have first defined a half adder first of all. Okay, fine. Next, so is there any other component we need to discuss here? No, actually another second component is also half adder, similar to that of the first one. So no need to discuss about anything about half adder because already defined. Now we have an OR gate. No need to define anything about the OR gate because it is a built-in primitive. So if anything is not known, then we have to define. So half adder is defined, built-in primitive is also known. Therefore, nothing to discuss about this thing, right? Therefore, finally, we need to write the complete full adder by using the half adders. Okay, first of all, what we have to do whenever we are writing a component, something like this, we need to write the test bench also. We need to verify this one, whether it is properly producing the output or not, we need to verify, right? So because this is the component that we are using the main module. For example, this module consisting of some kind of errors, for example. So then we are not able to construct the full adder correctly. Okay, so therefore writing the test bench is also it required, but we don't want to discuss about this one. Okay, but anyway, we want to verify this one. Now we are going to write a full adder. Okay, next we write a module full adder FA underscore gate level modeling. What is the contents that it is having? So the full adder consisting of what is the contents I'm writing here. So the full adder is something like this, having 3 input signals, A, B, C. This is the sum signal I'm using. This is what C out I'm using, right? Okay, I'm writing here A, B, C, sum, C out. So be careful about whether you are writing the sum, S is capital letter or small letter. Okay, C is capital letter, small letter. If you're writing the capital letter initially, then you have to write the capital letters throughout the program. Otherwise, small letters you write. Okay, so don't forget about this one. Verilog is a case sensitive. So the inputs are A comma B comma C. The outputs are sum comma C out. That means my intention is that first S is a capital letter, C is a small letter, but you write all small letters only. The usual practice, we write capital letter the first. Okay, fine. Now what we have to do now, so this is what is the inside of this full adder, FA? Inside of the full adder is this module. So this is the circuit diagram, right? So therefore, better I want to copy this circuit diagram. Copy and then paste somewhere else. Okay, so here I'm going to use my module so that I'm able to okay, I hope it's clear. Now I need to call half adder, right? So what is the name that I have given the half adder? Half adder I have given as, in the previously what is the name that I have given? HA underscore GM. I need to call HA underscore GM, same name that I have to use. So the name of the module is, for example, M1, component is M1. Okay, component. Okay, what is there inside of this one? That's what we have tried first of all. Okay, what is the first letter that it is saying that this is actually a input, first input, second input, third one is a sum signal, fourth one is carry signal, right? So let us write first this half adder. Okay, so HA. So what is the name of this HA? It's module 1. So it is called M1 I'm talking about. This is M1. This is called M2. Okay, So otherwise, if I want to write HA is my component name, you can also write it there. So నాకు confusing on the you can write HA. Okay. Here also you can write HA directly. So HA I'm writing. HA is actually module number 1. HA is the name of this module. Okay. What is the input? First input ఏమవుతుంది దీనికి? What is the first input? Is nothing but A. For this one, first input is A. So A is the first input. What is the next input? B. What is the sum output? Sum 1. Okay, it needs some kind of spacing, right? Okay, so next one is sum 1. Sum 1. Next one is Cout. Cout 1. So this is how I have written. This is the first module. Similarly, I need to write for the second module. HA. The name of the module is M2. Okay. So what is the second module says that M2? M2 input manaki ikkada. So sum 1, right? Sum 1. What is another input? C is directly coming from outside. What is the output for this one? Sum. What is the output for Cout for this one? Cout2. Cout2. Okay. A, B, C. Right? Is it clear? 2 half adders I have written. And one OR gate is also there. So that is a keyword, right? Therefore, keyword means OR gate I am writing. Let us consider this is called G1, gate number 1. For this one, what is the syntax for this one? First, I need to write the output for this one. Cout I need to write first. Then one input is Cout2. Another input is Cout1. That's all. Finally, we need to write AND module. Finally, we need to write AND module. So it is the writing the program is similar to that of the gate level modeling only. But the gate level modeling we use the gate primitives, but the structural modeling we use the components. So interconnection of the components. That's what we have to remember. I hope you can understood this programming language. So one important point we forgot. So far A, B, C that we have written, fine, we don't have any problem. But what about sum 1, sum 2, Cout2? Those are all internal to the circuit, right? So I need to write, those are all wires. Wire sum 1, Cout1. I'm writing the colors means you can understand clearly. Once when you look at this one, you can understand clearly. That's the reason why I'm writing the colors. No other meaning. But purple color, whatever I'm writing, that is actually a keywords that we should remember. Whenever I'm writing the purple color, that is meant for keywords. Other colors I'm using intentionally. That's all. So this is what we need to write the Verilog program for full adder using structural modeling. Is it clear to all of you? Any doubt about the structural modeling? Okay. Now we need to write this. Of course, we have written the full adder by using the structural modeling, but we want to verify this one. That means we need to write a test bench for the full adder. Okay. If thoroughly tested, the half adder is thoroughly tested, then it's fine. But we want, our main objective is that we need to verify the full adder. We need to verify the full adder. Okay, therefore we need to write the test bench for the full adder now. Okay, everybody knows how to write the Verilog program for the full adder. Okay, it has got 3 input signals. Okay, and we use the notation called. So simply I'll write for sake of completeness. I'm writing the test bench. Okay, what is the test bench of this one? Let us write module. It is called test underscore FA underscore GM. That's what I want to write. The inputs are rich data types A comma B, A comma B comma C. Okay. Next, outputs are represented by white data type, that is called sum and cout. Okay, what is the name of this module? FA underscore GM is the name of the module that I want to test. Okay, FA underscore GM is the module that I want to test. It's a module actually, M1. Okay, so what is the first variable that I'm writing? A, B, C, sum and carry, right? A comma, B comma, C comma, sum comma, cout. Okay, now, so initial statement, I need to use it for test benches or test vectors. Let us begin here. Okay, so simply I'll write, okay, for the simple notation is, um, first I will initialize with A is equal to, sorry, A is, sorry, concatenation of A comma, okay, B comma C is equal to 3 bit of all zeros. Okay, of course we need to write in this way. We need to write 8 combinations, right? Okay, better we need to write 8 combinations. Is there any good method is there? Okay, in this conventional method you know very well. I want to write it in a different way. Okay, please look at this thing very carefully. Okay, please understand this one very carefully. Uh, I'm modifying this a little bit. I'm modifying a little bit this. You know very well how to write the Verilog program for this one. You have to write 8 combinations and monitor everything. I want to modify in this way. Please remember. I want to change this one by vector notation. Okay, so this is actually 3 down. Sorry, I want to do 2 down to 0 of A. Okay, and sum and carry, I want to make it use it, say as it is, does not have any problem. Okay, so in this module, I want changing like this. So very carefully you listen. First A, B, C. Okay, so A, B, C, I'm writing in this way. Instead of that one, A of 0, A of 2 is the first one. Next, A of 1 is the next one. A of 0 is the next one. Why I'm writing, why I'm not writing A directly? A is actually 3 bit size I have given. But here as I'm writing directly, why can't I write directly A? Because previously what we have written, here the scalar notation we have written first, how many ports are there? 1, 2, 3, 4, 5. 5 ports are there. 3 are the input ports, 2 are the output ports. Okay, that means whenever we are calling this function or module, the same size that we have to mention individually. That means now this A of 2, now this A of 2 will be mapped, A of 2 will be mapped to A. If A of 1 is mapped to B, A of 0 is mapped to C. Therefore, individually each and everything will be mapped directly. So therefore, I have to write like this instead of A directly at this module level, right? So therefore, we have to be very careful about it. Okay. Now, next we are going to write sum signal, sum, and we are going to write cout. Okay. So why I'm not going to write sum and carry is also a vector notation, because in the test vector, I don't want to mention sum and carry. So whatever it may be, let it be like that only. It doesn't matter. But I want to mention by using the inputs only I need to mention. That's the reason why I am making use of facilities in the Verilog. Okay. Now it is possible to write, no need to write like this. So initially A is equal to 3 bit of all zeros, fine. Now I am going to use an always statement. Okay, I'm going to use always. Always for every 2 nanoseconds, A is equal to A plus 1 bit of 1. Okay, that's it. Okay, therefore A will be incremented every time. Therefore, A of A is nothing but A of 2, A of 1, A of A naught. According to that particular vector, it will choose that one. Okay. So therefore, finally, we need to write initial statement. Initial Okay, dollar monitor, I am going to write dollar monitor. Of course, everyone knows that, this one. Okay, so I want to mention the time. Time is equal percentage of b, sorry, t. A is equal percentage of binary. Sum is equal to percentage of binary. Carry C out is equal to also a percentage of binary. Okay, so after completion of that one, I want to write dollar time, a comma sum comma C out. These are the variables I'm using. Fine. So that's all. Finally, we need to write end module, right? End module. That's it. So I have written very effectively the test bench in this way. Instead of writing the 8 lines, 0, 0, 0, 0, 0, 1, 0, 1, 0, something like this, I need to write 8 like, right? So, but I have to use in this way, right? Fine. So this is how we need to write the structural modeling. So we take another example, okay? So that you can, shall we write the expected output so that it is also useful for you? What is the expected output? What is the expected output? First we are writing the time, right? ఇక్కడ మనం ఏం చేస్తాం, ఫస్ట్ టైం ఉండమని చెప్పాం, ఇక్కడ టైం చెప్పాం, తర్వాత ఏ రాయమని చెప్పాం, తర్వాత బి రాయమని చెప్పాం, సారీ సమ్ రాయమని చెప్పాం. నెక్స్ట్ థర్డ్ వన్ ఈజ్ సి అవుట్. సో వాట్ ఈస్ హ్యాపెనింగ్ హియర్ నౌ? At the time 0 nanoseconds, this will be activated. Okay, so at 0 nanoseconds of time, a is equal to 3 zeros, and this is applied on the module, and it will produce the sum is equal to 0, carry is equal to 0. Next, another 2 nanoseconds, that means 0 plus 2, but 2 nanoseconds. At 2 nanoseconds, a is incremented by 1. A is incremented by 1 means 0, 0, 1 will be there. Okay, now this is connected to the C of the module, this is connected to the B of the module, this is connected to the A of the module. Okay, but this is generated from the test bench. Now the simulator will produce output for this one is, output one is this is 0, sorry, this is 1, this is 1, this is 0. Another 2 nanoseconds. So that means since it is an always block, another, it wait for another 2 nanoseconds. So it wait another 2 nanoseconds means 3 nanoseconds, for 4 nanoseconds. Okay, so what is the value of this one? This value is equal to 0, 1, 0 added. So therefore the now last bit is connected to C, this is connected to B, this is connected to A. Therefore again this is applied on a circuit, and it will produce sum is equal to 1, carry is equal to 0, etc. Okay, so that's how it produces. It produces in this way. I hope you can understand this concept. Okay, now can you write Verilog program? Write a Verilog program for 4x1 mux using 2x1 mux. Use the basic gates. Use the for the 2x1 mux, you can use the basic gates. Okay, but you have in your hand, you have a 2x1 multiplexer, and I'm asking you to write the Verilog program for 4x1 mux. That means you have to design the 4x1 mux by using the 2x1 mux, and then for the 4x1 mux, you have to write a program, right? So please try to do it quickly. So the moment whenever I am talking about a small components in order to construct a big component, big system or big circuitry, obviously it involves the structural modeling. That's what you need to remember. Okay, please try to do it quickly. Okay, so let us write. I'm going to give you the hint for this one. For example, we have a 4 cross 1 max. Okay, that is called 1, 2, 3, 4, 1 and 2 selection lines, 1 is output. Therefore, this is called I naught. For example, I1, I2, I3. This is a selection line 1, selection line 0. This is a Y. It is a mux underscore 4 plus 1. Okay. Okay, it's better to consider the vector notation for this one. Okay, what is the vector notation for this one? I'm going to consider the vector notation. So this is actually a 4-bit size of I. This is a 1-bit size Y. This is a 2-bit size S, right? It is a mux 4 cross 1. Okay. So this is a vector notation. It's better to write in the vector notation, right? So what is the structure for this one? How do we develop this 4 cross 1 multiplexer by using the 2 cross 1? Okay. So let us consider in this way. 2 cross 1 max. It allows 2 input signals, but we need 4 input signals, right? Therefore, we have to use another 2 cross 1 max. Okay. So thereby we have a signal, 2 signals are available here, another 2 signals are available here, right? So this is nothing but I of 0, for example. This is since I am writing the vector notation, right? I of 1, this is I of 2, this is called I of 3, right? Now, so I am going to produce only one output signal from this and this one, but it will be converted into another only one input, one output by taking another 2 cross 1 multiplexer. Okay. So here, this is output Y. This is the output Y. Okay. So in this situation, what I'm doing here is that first, the selection lines I need to choose, right? So if I not wants to go to the output signal, what it has to do? So the first, this signal has to be generated. This line must be active. Okay. Then this line must be active. So this line must be active. That means this line must be disabled. The మొత్తం disable అయిపోవాలి. So therefore, what I'm going to do here is that I'm going to use a selection line something like this. Okay, so let us write a test bench, this one. For example, S naught, S naught, S1, S naught. For example, Y 0 0 0 1 1 0 1 1. Okay, this is called I of 0. This is I of 1. This is I of 2. This is I of 3. Right. So therefore, if I naught is selected, that means I naught I1 must be selected, means this will be connected at this point, right? So that only the first thing will be selected. Okay. In the second, that means here and here for this one and as well as this one. So for this one, just I'm writing this one and when this one, both requires S naught. Both requires S naught. See here what will happen. If suppose this is 0, this is 0. Okay. I naught will be selected. That means this 0 means this will be selected. Okay. And it is not at all selected. If it is not selected, means we don't bother about this multiplexer. Second multiplexer, we don't bother about it. Upper multiplexer is important. So if it is 0 means I naught will be selected. Therefore, I naught will come as an output signal. For example, it is 0 and this is 1. Here also, only this is active, but this is not active. So therefore, again, it consisting of S naught is equal to 1 means this line will be active. Okay. Initially, this is active, this is not active. Now, this is not active, this is active. So it will go, I1 will go and output. Similarly, this is 1, 0. Something like this, it will be going and output. Okay. So we don't bother about this thing. Okay. Fine. So the design is completed, but I want to describe it by using Verilog programming. Okay. So therefore, this is what the inside of your module. Okay. Now I need to describe this one. So what is the first step? What is the first step I need to do? I have to write the Verilog program for, I think with a little bit, without any complexity, I want to remove this one. I want to say this is S0 and this is called something like this. Okay, first I need to write the 2x1 multiplexer definition. I need to write the 2x1 multiplexer definition. This is called mux 1. I think it is mux we will write. Okay, mux 2x1 is better to write 2x1. Okay, so therefore three 2x1 multiplexers are available. All are same type. That's the reason why one time I want to define. Okay, so let us define once the multiplexer. So as all of you know that what is the multiplexer size? What is the multiplexer? So within another 15 minutes I will complete it. Okay, please wait for 15 minutes. So this is actually I, this is actually Y, this is actually selection line. This is called mux 2x1. Okay, same name I can use, it doesn't matter. I'm using I. Suppose I'm not interested to use this one. So better I want to use some A, some Y I want to consider. For example, something like this. Okay, same name also we can use it, but don't worry about it. So let us write better for the first time, don't confuse X, for example, Y. It is some example S only. Okay, fine, no problem. Write module mux underscore 2x1. So that's the way I'm writing. That's the way I'm writing. So what are the variables I'm using here? Also vector notation S comma Y. Inputs are 1 down to 0 of X. Output is Y. Another input code on the other one. We have another input S. Right? Fine. So what is the how do we define this one with the help of gate level modeling? Of course, a different way I'm writing. So please look at this one. We have an AND gate. We have another AND gate. We should have an OR gate, right? So it requires X0 is required. Okay, but it requires, yes, it requires X of 1, but it requires S complement, right? S complement is required. So this one and this one, take it as an output is 5. Is it clear? So I'm going to write this one. First G1 I'm writing. Let me consider this is called G1. This is called G1, G2, G3. G1 ఏమవుతుంది బాబు ఇప్పుడు మనకి? It is an AND gate. The name of the gate is G1. Okay. Now inputs are, how do we write the inputs here? First one is the output I need to write. Here I need to output. What is the output? I don't know. For let us example take T1. T1 is my input. Okay. And then I need to write one input is X of 0. Another input is S. That's all. You take another AND gate. See here carefully understand how I am writing. G2. T2 I'm writing for this one. This is called T2. So for example, I'm writing T1, T2 directly. This is called T1. This is called T2, internal to the circuit. Now, not X of 1 I'm writing. For S, not of S I'm writing in this way. Please remember what I'm writing here. Instead of taking the NOT gate separately, there is a provision is that by using the operator called negation operation, negation of S. Okay. So this is the negation of yes, negation of yes. Clear? So for that one, I know I don't want to use any other thing, right? Finally, I write and module. So voids are required. Voids are T1 comma T2. Okay, that's it. So this is how I have done my 2x1 multiplexer definition. Okay. Now I need to write this one. I am going to use this component to construct a 4x1 multiplexer. Okay. So therefore, let us draw the, let us do this one also again. Okay. So this is the component that I am going to use. Okay. Copy and then paste it somewhere. Okay, this is what I'm going to describe. Okay, so let us give the what is the name of this module. Okay, so 4x1 multiplexer, 4x1 max. I'm going to construct. Okay. Yeah, sorry, we need to define G3 also. I forgot to write the G3 also. It is an OR gate, G3 also. G3 is nothing but y comma T1 comma T2. Okay, G3 have to define. Okay, but S bar, for the S bar NOT gate is required. That NOT gate is not required to do this one because already we have used that negation. Fine, thank you very much. Okay, next we'll start the module numbers, module name. This is called module. It's a mux underscore 4x1. See, I'm not writing 4x1 multiplexer something like this. 4x1 mux I'm not writing. Why I'm not writing? Because it's an identifier. Identifier should not start with number. That's the reason why I don't want to write. But somehow I want to mention the 4x1 mux. Okay, 4x1. So for that one, I'm using here after the first statement, wherever you are writing the number, it is possible to write, right? Fine. So here is a vector notation I'm using I, S, Y, right? So in this inputs are 3 down to 0 of I. Another input is, it is 1 down to 0 of S. Okay, so I think it is also better you should write this is S of 0. This is S of 1. Okay, don't forget. Next, another one is nothing but output Y. Fine. Now we need to call multiplexers. So how do I call these multiplexers? By its definition. So how I have defined this one? This is the way that I have defined. So I need to call that one. Simply mux max underscore 2x1 I have written. This is the module number 1, M1 I am considering. So what is the first thing actually I have to write? X I need to write. X means it's a 2-bit size, right? So therefore, multiplexer of 2-bit size I need to consider. Okay, I have to write I of 0 down to 1. Okay, 0 down to 1. Okay, sorry. Better I need to consider 1 down to 0. No. Just we have to write 0 down to 1. 0 down to 1 means first one LSB అనేది ఎక్కడ ఉంటుంది కదా, better write 1 down to 0. Okay, so 0 is LSB, 1 is MSB. Okay, it's 2-bit size that is copied with 2-bit is mapped with this X. Okay, so therefore that means that X is mapped with I of 1 down to 0. Clear? It's mapped. Now we need to have a single information for this one. Okay, what is the data component that we need to have? So this is required. This is actually S of 0. Therefore we need to write S of 0. What is the output for this one? we need to write an output for this one, right? Y means here the output is required. So what is the name? Let us give, for example, T1. This is T2, for example. T1 I'll write. I hope you understood this concept. Okay. Now we have another multiplexer. Write another multiplexer. Mux underscore 2 cross 1. This the name is M2. Okay, we start. For this one, what is the notation that I have to use? I 3 down to 2, right? This is called part selection. So we have actually a 4-bit size I. Okay, I is actually a 4-bit size. I is actually a 4-bit size. Okay, that two parts we are taking here, another 2 parts we are taking in the second module, right? So that's what we need to consider. Now, what is the S here now? This is also S of 0 only, but this is T2 will be assigned to this one, right? T2 will be this thing. Fine. Now, last third one. See, so very carefully you have to write mux underscore 2 cross 1. This is called M3. So, చూడండి ఇక్కడ జాగ్రత్తగా. So actually T1, T2 are represented by the vector scalar notation. But somehow I have written the scalar notation, but I want to use the same way. So, but I cannot use like this. So T1 comma T2 comma S of 1 comma Y. I should not like this. Why? Because the first position is mapped to X is equal to T1, but both are not equal. Both are not equal. Why? Because it is a 2-bit size, right? It's a 2-bit size, but here is a 1-bit size. Both are not equivalent. Okay, that means that there is a mismatch between the ports. Mapping is mismatched. Okay, so therefore what should I do? Instead of taking the individual lines, I want to combine and make it as one. Okay, so for that one, I am going to use the concatenation operation. Simply, I am going to write concatenation of T1 comma T2. Concatenation of T1 comma T2. Is it clear now? Now, this concatenation operation of T1 comma T2 is equivalent to say that it is mapped with the 2 cross 1 multiplexer that we have done earlier. Okay, now it becomes a 2-bit size. Now this is also a 2-bit size. Okay, does not have any problem now. Clear? So this is how we have to do this thing. Okay. So therefore, this is what that is acceptable thing. So in the earlier one, it is not acceptable thing. It is acceptable thing. It is acceptable thing. But sorry, T1 is not equivalent to X because it's a 1-bit size. It is a 2-bit size. So it is not at all acceptable. That's the reason why concatenation operation I have used it. So everything is written. Finally, we need to write N module. Okay. So T1, T2 is not declared. So I want to write T1, T2, while T1 comma T2. Okay. That's it. So you may ask the question, sir, why can't we use the T1, T2 also a vector? Yes, you can write the vector also. There is no problem. But you have to change here the first multiplexer M1 module. For M1 module, instead of the T1, T of 1 we have to write. Here is the T of 2 that we have to write. And here we have to write a T of 2 down to 1 we have to write. But here no need to write on this one, no need to write a concatenation operation. For the M3 module M3, no need to write the concatenation operation. Directly we can write T itself. Okay, so that is what we have to remember. So this is how we need to write the structural molding for this one. Okay, so these 2 basics that you should know carefully, and this is more than sufficient to write any system having the different components. Okay, so with this we have come to the end of the session. Tomorrow we will see the gate delays and some more detailed discussion about the structural modeling and gate delays. With that, we can complete the gate all modeling. Okay, we have to write the test bench for this one. Take it as an assignment. Take it as a homework. Write the test bench for this 4x1 multiplexer. Okay, so see, the writing the test bench for the forecast one multiplexer is unique. How we are designing the forecast one is not a matter for us. Okay. So, but test bench is unique for whatever the modeling style that you're using for designing of the forecast one marks, or maybe full adder, or maybe something else. Okay. Please remember that. So thank you very much, and we'll see you in the next class. See,